Let us now look at the last topic we would like to cover in this set of videos. We are going to look at numerical differentiation. So the scenario is like this. We are given the following data in the form of a table. So basically you have the dependent variable to be f of x. You can call it y is equal to f of x. So you can either call it y or a function of x. The independent variable is x. So this function, right, what is given to us is x varies from 0 to 0.8. So only specific values are given. So at x is equal to 0, f of x or y is given to be 0.2. So this is this point. And then at x is equal to 0.12, it takes a value of 1.309, and x is equal to 0.22, it has got a value of 1.305, etc., etc. At x is equal to 0.32, it is 1.7433, things like that, right? So that is the tabulated data that is given. Kindly note, this is not equally spaced data. So the gap between first x value and the next x value is 0.12. Between the second x value and the third x value, the gap is 0.1. 0.1 here, 0.06 here, and 0.1 here. So what I'm trying to say here is that the data that is given to us is not equally spaced x data. Nevertheless, we are given the values of x, the independent variable, and we are given the corresponding values of y, or what is denoted as f of x, which is going to be the dependent variable. Now the question is, we are asked, given this table, we are asked to find out the value of df by dx, right? So we are asked the value of dy by dx if you like, or you can just say since y is equal to f of x, we are asked df by dx at x is equal to 0.4, right? So that is what is being asked. We know the value of x at 0.4, that is what is given here. But we are asked to find out the value of df by dx, the derivative of the function f at x is equal to 0.4. Now please note that this data has been obtained from this equation. So this is the truth. This is the equation that generated this data. So if we knew this equation, then we can use our high school calculus to find out the derivative of the function and evaluate it at x is equal to 0.4 and get the answer. All right. So one route to get the answer to the problem is to fit a polynomial to this data set, right? So we can always fit some polynomial. The command in MATLAB, if you want to fit polynomial function to this data, is called polyfit. So kindly try using a polyfit function. If you fit a polyfit function of order 5, you will get this equation. Then using high school calculus or using what I'm going to illustrate here, symbolic computing in MATLAB, you can find out the derivative of the function at x is equal to 0.4. So that is one way. Take the data, derive a mathematical model out of it, and I've said polyfit can be a function that can be used for this purpose. Other choices are equally possible. So you get the function and then you can solve the problem. The other route is to get it from the data itself using a variety of approximations. So I'll just demonstrate those things to you here. So here I'm going to assume first that I've taken this data and I've used the polyfit function and I've fitted a function of order 5, right? So I've just used polyfit and I've said I want a fifth order polynomial to be fit to this data, and out comes this value. Okay, so kindly do polyfit and then see that you get this answer. Or just say you know the function form, right? Then what you can do is you can use symbolic computing in MATLAB. So I go to either a M file and I just say sims x, and then the second line, etc. So if inside a M file, right, if I'm using an M file, I will not use this MATLAB prompt, as you may imagine. You just type in this function, these commands, right? You don't use this double MATLAB prompt. So whenever I use double prompt, right, the MATLAB prompt, this thing, it means I'm doing these things on the command window itself directly. I'm not writing an M file. So I say sims of x to just announce to MATLAB that x is a symbol. SYMS is symbols. So I can define one or more symbols using the sims command. Here I've just defined one symbol x. And then I say diff, that means differentiate. DIFF is a MATLAB command in the symbolic computing toolbox. So I say differentiate this function. So I say 0.2 plus 25 times x. So while writing, we write it as 25x, but in MATLAB, you should say 25 star x minus 200 star 200 times x squared. So x to the power of 2 and so on until we come to 400 times x to the power of 5 and then ordinary brackets close to kind of match with this brackets open here. You do the closing brackets. So when you do it, what it does is it symbolically differentiates this and gives this to be the answer. For example, 0.2, right? When you differentiate it will become 0. 25x, when you differentiate with respect to x, it's going to be 25. Minus 200x squared, when you differentiate with respect to x, is going to be minus 400x. That is what you see here. And 675x cubed differentiated with respect to x is going to give you 2025 times x squared. And minus 900 times x to the power of 4, when you differentiate with respect to x, will give you minus 3600 x cubed. And 400 x to the power of 5 upon differentiation with respect to x will give you 2000 x to the power of 4. So it's 5 times 400 and times x to the power of 5 minus 1. Okay, we all know that. So this is what MATLAB computes for us when you use the diff command. So the answer that you get is basically the derivative. Now I'm just saying substitute. SUBS is substitute. In the answer, that means in this expression, right, which is now the answer A and S, at this stage, right, this is what is contained in answer. So it's going to be this. So substitute in this answer variable x, for x, substitute the value of 0.4. And then you will get this to be the answer. When you press enter after typing out that command, the answer comes out to be 49.5, which will still be in symbolic form. So if you want to convert it to a number for further processing in MATLAB, you will just say evaluate, right? Answer. Evaluate answer means now this is the answer, right? It is not in numeric form. It is in symbolic form, though it gives you as 49.5, which we know is equal to 9.8. But then inside MATLAB, if you want to convert this object, which is in symbol, to a number, you just say eval ans. So eval means evaluate. So it gives you 9.8. So the derivative of the function at x is equal to 0.4, it is 9.8. That's the value. So this is called the analytical value or the true value of the derivative. Why do we say this? It's a true value because we know the true function in this case. Okay, and therefore we are getting this answer and we say this is the true or analytical value of the derivative. All right. But then if you fit a third order polynomial to this data, or if you fit a seventh order polynomial to this data, the answer could be different. Right? It just happens for illustration purposes. We know what is the true function here. But in reality, nature will hide it from us. All we have is data from a system like this. So we can fit either a second order polynomial or an eighth order polynomial to this data and then repeat this process, right? And then just do this process to get the derivative, all right, of the function. Same set of commands, but we might have a different function here. So you might get a slightly different answer here. So I encourage you to try that. Sometimes you might get the same answer. But all I'm trying to say here is this answer is the true answer to this problem because we know the function. If you had gone for a second order polynomial fit or a seventh order polynomial fit to this data, you might get a different answer, right? But anyway, this is one route to take the data, convert it into a polynomial and use the symbolic processing toolbox in MATLAB, you can get the answer. So for now, our benchmark is 9.8, right? So this is one route to get the derivative at x is equal to 0.4. Now the other route is we can use this concept of finite difference approximation, right? So we are trying to get a estimate of the derivative. So I put f dash. So if I put f dash means it's the first derivative. If I say f double dash, it means the second derivative and so on. So we are trying to find out the derivative of the function at x is equal to 0.4. And the idea is you can have different approximations, right, to functions or the derivative of functions. So the idea is you can have different approximations to the derivatives of functions. So the first approximation we are going to look at is what is called the forward difference approximation, or FDA. Please note the definition in calculus is df by dx, right? df by dx is equal to f of x plus delta x minus f of x divided by delta x as delta x goes to 0, right? So it should be as delta x goes to 0. That is the very important stuff. So this equality holds when delta x goes to 0. Basically, this is the gradient of the function, right? So you are at x, you are going to x plus delta x, right? So this is x, you are going to x plus delta x. When you do that, y goes from f of x, y goes to f of x plus delta x. So this value is f of x plus delta x, right? In other words, it's like this. X is equal to x is here, x is equal to x plus delta x is here. The value of the function is f of x at x is equal to x. So this is f of x. The value of the function at x plus delta x in this illustration is here. So this is f of x plus delta x, this value, right? This is f of x. So the gradient, the derivative, the slope is the vertical height that you gain as you move from x to x plus delta x, and divided by the amount you move in the x direction. So that gives you the slope, right? The vertical height gained or lost as you move from x is equal to x is equal to x plus delta x. So this is what is called delta y, the change in y. This is the change in x. So delta y by delta x is the slope of this line, which is the derivative of the function at this particular point. So you're looking forward, right? You're at x, you're looking forward to x plus delta x, and then you are finding out the change in y divided by the change in x. And when the change in x is infinitesimally small, df by dx is exactly equal to what you see here. All right. So the numerator is delta y, the denominator is delta x. So you get dy by dx is equal to delta y by delta x as delta x goes to 0. But when delta x is not 0, right, is not so small, then I can put an approximate symbol here. Instead of the equality symbol here, I can put an approximation symbol there. So df by dx, when I look forward, that is going to be equal to this f of x plus delta x minus f of x naught divided by delta x. So that's the forward difference approximation. Please note, for this particular question, I have carefully chosen the point at which I'm asking the derivative, right? I've asked the derivative at x is equal to 0.4. If you look to the left of 0.4, the value of x is 0.36. So the gap is 0.04. If you look to the right of 0.4, the data given to us is that x is equal to 0.44. So the gap between x and x plus delta x is also 0.04. So this is a good point to illustrate the ideas because we are doing numerical differentiation for the first time. If on the contrary, I had asked you a question, what is the derivative at x is equal to 0.7? If this became our query point, this gap to the left is 0.06 magnitude, right? 0.7 minus 0.64 is 0.06. The gap to the right of that is 0.8 minus 0.7, which is going to be 0.1. So it is unevenly spaced data, so that we have to have a reasonably more careful analysis of this problem. So the question I've taken is just to make things quite simple for us. In any case, df by dx is approximately equal to, right? So it should be approximately equal to the function value at x naught plus delta x. So x naught is 0.4 because we are trying to find out the value of the derivative at x is equal to x naught. So x is equal to 0.4 means x naught is 0.4. And delta x is 0.04 here because the next data point in our table is at x is equal to 0.44. So we are looking at the value of the function at x is equal to 0.44. So minus f of x naught. So the value of the function at x is equal to 0.4 divided by delta x. Delta x is 0.04. All right. So when you put in the numbers from the table, the value of the function at x is equal to 0.44 is given here to be 2.842985. Okay, that value minus the value of the function at f is equal to 0.4, that is given to be 2.456000. So that is what this is. And then the delta x is 0.04. That means 0.44 minus 0.4, which is 0.04. So when you do that, you get this to be the answer. So this is one approximation of the derivative at x is equal to 0.4. Now, instead of looking forward, you can always look backward, right? So basically you are here at x is equal to 0.4 in this example. I can always look behind. And the data point that's available to us is x is equal to 0.36. So this gap is 0.04. The delta x is 0.04 even here. But we have the value of the function here. We have the value of the function here. Um, right? So this axis is f of x, as you can easily imagine. So these are the two values of the function. Instead of looking at the right hand side of 0.4, I'm going to look backward. That means to the left of 0.4, pick up a point, the next point there, and then assume the relationship between these two data points. The relationship is linear, and therefore I can estimate the slope of this line. So again, using backward difference approximation, which is called BDA, we get df by dx is going to be f at x naught minus f at x naught minus delta x, with delta x being 0.04 here. All right, so the function now, the approximation is f of x naught minus f at x naught minus delta x, right? Because we are looking at the left, divided by delta x. So the forward difference approximation is this. Looking forward, looking backward, one could write an expression like this. So when you substitute the numbers from the table for f at x is equal to 0.4 minus f at x is equal to 0.36, you will get 9.52, which is a different answer to the problem, right? It is this is what forward difference approximation gives us. This is what backward difference approximation gives us. So you can have higher order difference approximations if you like. Okay, so you can improve the accuracy by increasing the computational effort. So please treat this as just an introduction to this field, right? And we'll look at more theory and more expressions for these derivative calculations. Now, one final thing is, why do we have to look either forward or backward? We can look at both sides. So the idea here is this. This is f of x. This is x-axis. So I'm trying to find out the derivative at this particular point. So I'm going to look at the next data point, which is at x naught plus delta x. So the value of the function is given here. I'm going to look at the point to the left of x naught, right, which is at location x naught minus delta x. And I'm just assuming delta x, as I explained earlier, is the same, 0.04. And it works out for this point. X naught is 0.4. We have data in the table at x is equal to 0.36 as well as at x is equal to 0.44. So delta x in both cases is 0.04. So I have the value of the function at this particular point, right? So this is the value of the function at x naught minus delta x. This is the value of the function at x naught plus delta x. So I'm using both points, one point to the right and one point to the left. And this becomes to be called as central difference approximation, CDA. So the expression is df by dx at x naught is approximately equal to. We have to do this approximately equal to because delta x is not very small. So it is approximately equal to the value of the function at x naught plus delta x minus the value of the function at x naught minus delta x divided by 2 delta x, because this gap is going to be 2 delta x. I'm going to travel 2 delta x from x naught minus delta x all the way till x naught plus delta x. So this is going to be 2 delta x. In moving 2 delta x, I'm gaining this amount, right? This is the amount I gain, which is delta y. Delta y is nothing but f of x naught plus delta x minus f of x naught minus delta x. So this is the overall gain I have in the height. So the height gained divided by the horizontal distance traveled is nothing but the estimate of the slope. So when I put in the numbers, I get the value 9.601. right? So there are many approximations available. We have seen 3 approximations, but we will see more approximations later. And you can have higher order approximations that can improve the accuracy to get closer to the analytical values, but then more computation will be involved. So always that is the case. If you are making your formulae a little more complex, you can gain in accuracy, but it will also increase the computational load. Now, in summary, we have, in the set of videos, we have solved some typical problems. We have been introduced to the kinds of problems that we will do. We'll get into the details of the mathematics and the algorithms behind these functions that have been introduced to you. Taylor series expansion of functions will be the key. Learning MATLAB is a matter of practice, practice, and practice. Like real estate, right? They say the key aspects are location, location, and location. So for learning MATLAB to mastering it to solve problems, the only thing that is required is practice, practice, and practice. So I'll try to do this in tutorial problems through our lecture videos, notes, and assignment problems. But you should develop the habit of taking some good textbooks in this area, or problems in thermodynamics or problems in other courses that you do. You try to make it a habit of solving problems using MATLAB. Okay, so that's the way to master it. All right, I'll catch up with you in another set of videos. Thank you for your time and attention.